Assalamualaikum and hi everyone. Okay, so this is the continuation for our previous video, which is on sketching titration curve. Okay, so this is your 6th video on chapter 7. So we're going to discuss on how to calculate the pH changes along the titration curve. Okay, so I'm going to discuss on 3 different examples. Okay, just like you are having your titration curve in 3 different sets, which is between strong acid and strong base, weak acid and strong base, as well as between strong acid and weak base. So we're going to discuss the same combinations of acid and base into this calculation of pH changes along the titration curve as well. Okay, so let's start now with our strong acid versus strong base. Okay, so this titration is between my hydrochloric acid and my sodium hydroxide. You're going to form sodium chloride salts with water. So I'm using 25 milliliters of 0.1 molar of my hydrochloric acid. So my hydrochloric acid serves as my analyte. So analyte means it is in the conical flask. Okay, then we're going to continue with titration with my NaOH. Okay, so this one acts my titrant. Okay, so you were supposed to calculate the initial pH of the analyte. So my analyte is my HCl. Okay, before the titration begins. And then the new pH after additions of 15 milliliters of my NaOH. And then pH at equivalence point and volume of NaOH needed. New pH after addition of 45 milliliters of NaOH. And then you are supposed to sketch the titration curve. Okay, so let's begin. Okay, so to calculate the initial pH of my HCl, which is our analyte, since this is a strong acid, so whatever initial concentration of HCl that is present, okay, it's going to be used to produce our H3O plus and equals our Cl minus, because it's a complete dissociation. So my initial is 0.10 molar. Okay, so that means at the final point, all the HCl will be converted to H3O plus. Okay, so your pH is negative log H3O plus, okay, which is negative log 0.10 and is equal to 1.0. So that is the initial pH of your analyte. Okay, next, when we already add 15 milliliters of NaOH, that means you need to find out the changes in the number of mole. Okay, so initial mole of my HCl, so mole is molarity, okay, time with the volume in liters. Okay, so you will get the initial mole of my HCl is to be 2.5 times 10 minus 3 mole. Okay, I add 15 milliliters of my NaOH. So molarity of NaOH is 0.1 molar times with 15 over 1000. You need to convert the volume into liters. And you will get the number of mole of my NaOH is to be 1.5 times 10 to the power of negative 3. Okay, so changes in mole depending on which number of mole is the smallest. Okay, and my NaOH has the smallest number of mole. So changes is negative 1.5 times 10 to the power of negative 3, as well as the negative for my HCl, because this is a neutralisation reaction. So we use up both HCl and NaOH. Okay, so remaining mole is initial mole minus changes mole or plus. Okay, so you will get here 1.0 times 10 to the power of negative 3, and we completely use our NaOH, so become 0. So final concentration, okay, since we only have remaining HCl in the solution, so final concentration is only for HCl, which is 1.0 times 10 to the power of negative 3 mole. Okay, final volume in the solution, we have initially 25 milliliters of my HCl. Then I add 15 milliliters of my NaOH. So in total, I have 40 milliliters of solution, which is 0.04 liter. Okay, so divide by 0.04 liter, you will get the final concentration to be 0.025 molar. Okay, and it is under HCl. Okay, so that means pH equals to negative log 0.025, which is equals to 1.60. So the pH, the new pH after additions of 15 milliliters of NaOH is 1.60. Okay, so what will happen at equivalence point? Okay, so we have 25 milliliters of HCl titrated with NaOH. Okay, so the titration reaction produce NaCl, which consists of Na plus and Cl minus. So Na plus is a cation from a strong base, NaOH. Okay, so it will not hydrolyze again in water. Okay, whereas Cl minus is the anion from strong acid HCl, therefore it will not hydrolyze again in water too. Okay, therefore pH of the salt at equivalence point will depend on the auto-ionizations of water. Okay, so auto-ionization water, we have water, okay, reacting with another water. So one will serve as acid and another one will serve as a base. So it's equilibrium reaction. So we're going to produce H3O plus OH minus. Okay, so Kw is consisting of H3O plus equals to OH minus, okay, which equals to 1.0 times 10 to the power of negative 14. So at equilibrium, we have equal concentration of H3O plus and OH minus. So therefore, H3O plus concentration is simply square root of 1.0 times 10 to the power of negative 14, which is 1.0 times 10 to the power of negative 7 molar. So your pH is negative log 1.0 times 10 to the power of negative 7, which is 7. So at equivalence point, okay, for this titration, the pH is equal to 7. Okay, so you need to find out what is the volume of NaOH needed for the equivalence point to be reached. Okay, so we're going to use this formula. M stands for molarity, V stands for volume, and this subscript A referring to acid, subscript B referring to base, and this big A and big B referring to the stoichiometric coefficient as you refer to the titration equation. So A again for acid and B again is for base. So molarity of my acid is 0.1 molar. Volume is 25 milliliter over. I'm using 0.1 molar of my NaOH as well. So V and NaOH equals to 1 over 1. So cross multiplication, you will get V and NaOH to be 25 milliliter. So my equivalence point will be reached when I add 25 milliliters of my NaOH. Okay. Alright. So now let's calculate what is the new pH after additions of 45 milliliters of my NaOH. Okay, so we have to calculate the initial mole of my acid and NaOH. Okay, so acid is a fixed volume, 25 milliliters. Okay, so you will have initial mole, the same number of mole, which is 2.5 times 10 to the power of negative 3 mole. Okay, so my NaOH is 45 milliliters converted into liters, times with the 0.1 molar. So you will get it to be 4.5 times 10 to the power of negative 3 mole. Okay, so changes in mole is the smallest mole. Okay, so smallest mole in this example is our HCl, so negative 2.5 times 10 to the power of negative 3 minus 2.5 times 10 to the power of negative 3. So remaining mole for hydrochloric acid is completely being used 0, whereas for my NaOH is 2.0 times 10 to the power of negative 3. Okay, so final volume of the solution, I initially have 25 milliliter of HCl. Okay, and then I add 45 milliliter of my NaOH. So in total now, I have 70 milliliter solution, which is equal to 0.07 liter. So the new concentration of my NaOH is 2.0 times 10 to the power of negative 3 mole divided by 0.07 liter, which is equals to 0.0286 molar. Okay, so our final concentration is in NaOH, which is our strong base, completely hydrolyzed. Okay, so going to form Na plus OH minus. So whatever the concentration of NaOH is present, so it's equivalent to the concentration of my OH minus, which is 0.0286 molar as well. So POH equals to negative log 0.0286. So it's equivalent to 1.54, and your pH is 14 minus POH. So 14 minus 1.54, which is equivalent to 12.46. Okay, so the new pH after additions of 45 milliliters of NaOH is equals to 12.46. Okay, you're going to use this information to sketch the titration curve, which looks like this. So we start with the initial pH of my analyte, okay, which is our strong acid, which is 1. Okay, and then it's going to have a sharp increase, which is our pH jump here, which is 3 to 11. Okay, and then pH at the equivalence point is 7. And we need, okay, it shouldn't be 20 here, it should be 25 milliliters of NaOH is required. Okay, and then it slowly increase until it never reach the asymptote of our asymptote, which is our initial pH of our NaOH, which is 13. So it will never cross the pH 13. So this point, okay, so this point is when we add 45 milliliters of NaOH. Okay, let's try with the weak acid with strong base. Okay, so we're going to titrate, okay, ethanoic acid with NaOH. Okay, so our NaOH serve as our analyte here because it already gives you the volume. Okay, so ethanoic acid serve as your titrate. Okay, so initial pH of the analyte is referring to initial pH of my NaOH. Okay, so let's try to calculate. Okay, so calculate the initial pH of the analyte in the conical flask, which is our NaOH. NaOH strongly is a strong base which completely hydrolyzed in water, forming. Okay, so if I have my initial concentration of NaOH to be 0.2, okay, so my final also 0.2 for my NaOH, which is Na plus and OH minus. So 0, 0. So POH is negative log OH concentration, which is negative log 0.20. Okay, so negative log 0. Which is equals to 0.70. So your pH is 14 minus 0.70, which is equals to 13.30. So that is the initial pH of your analyte. Okay, what will happen after additions of 10 milliliters of CH3COOH? Okay, so you need to calculate the initial moles of your CH3COOH. Okay, since this is a titration between weak acid and strong base, so we're going to include our salts concentration into the calculation, because at one point when we have both weak acid and our salts, they will behave like a buffer system. Okay, so calculation of the pH of the buffer system will require a different formula, which you're going to use Henderson-Hasselbalch equation. Okay, so let's calculate initial mole of our ethanoic acid. So we add 10 ml, okay, so 10 over 1000 liter times with 0.4 molar. Okay, so it's equivalent to 4 times 10 to the power of negative 3 mole. So my NaOH is 40 over 1000 liter times with the concentration 0.2 molar, which is equals to 8 times 10 to the power of negative 3 mole. Okay, so we don't have our sodium ethanoate at initial mole. So changes in moles referring to the smallest mole. Okay, the smallest mole is my ethanoic acid in this example. So negative 4 times 10 to the power negative 3 mole. Okay, whereas for our sodium ethanoate, it's going to be positive because we produce it through the neutralization reaction. So 0. And this one leave out 4 times 10 to the power negative 3 mole. And plus 4 times 10 to the power negative 3 mole. Okay, so we have 40 milliliters of my NaOH plus with 10 milliliters of added ethanoic acid. So final volume of the solution is 50 milliliters, which is equal to 0.05 liter. Okay, so final concentration is in NaOH, which is 4 times 10 to the power negative 3 mole divided by 0.05 liter. Okay, so you will get the molarity in the terms of mole per liter, which is equals to 0.08 molar. So this one is 4 times 10 to the power negative 3 mole as well, divided by the volume. Okay, so we'll have 0.08 molar as well. Okay, but it's in the solution we have excess NaOH and our salts that is forming. So they cannot work as a buffer component because it does not have common ion between them. So the calculation of pH is just simply based on our NaOH. So pOH equals to negative log OH minus, which is our pOH is equal to 1.10 and pH is simply 14 minus pOH. So 14 minus 1.10, which is equivalent to 12.90. So this is the new pH of the solution after additions of 10 milliliters of ethanoic acid. Okay, so let's now calculate the pH and the volume required for the reaction to reach equivalence point. Okay, since we produce, it should be CH3COO-Na, which is our sodium ethanoate. If we're breaking it down, we're going to have Na plus ion and CH3CO minus. So Na plus is a cation ion from strong base NaOH. So it will not hydrolyze again in water. Okay, whereas this ethanoate is a conjugate base from weak acid. Okay, so it will hydrolyze again in water. Okay, so you're going to write down the hydrolysis equation. So CH3COO negative equals plus water So throughout the reaction, we're going to produce hydroxide ion, which is the properties of a base. Therefore, pH is more than 7. Okay, so how much NaOH is needed to reach the equivalence point? You're going to use this formula. So I have 0.4 molar. Okay, it shouldn't be NaOH, it should be CH3COOH. Okay, so we have 0.4 molar of CH3COOH, volume of the acid to be found, okay, over 0.2 molar of my NaOH time with the volume of NaOH used is 40 milliliter equals to 1 over 1. Okay, so cross multiplication, you will get your VA, okay, volume of the acid needed to reach the equivalent point is equals to 20 milliliter. So after additions of 20 milliliters of my ethanoic acid, equivalence point has been reached. So that means the titration has goes to completion. So after that, if more than 20 milliliters of ethanoic acid has been used, so means all the NaOH has been used up and been converted to form our sodium ethanoate salts and water. So after more than 20 milliliters of ethanoic acid is being added, so now the solution contains a mixture of our weak acid, which is in excess, with our salt. So they're going to work as the buffer system. Okay, so this one, we have 50 milliliters of ethanoic acid being added. So right now, we are having more or excess weak acid because we only need 20 milliliters of my ethanoic acid to completely neutralize my NaOH. So more than 20 milliliters of ethanoic acid has been added. So the remaining is known as excess amount. So in the solution now, we have excess weak acid with our sodium ethanoate salt. So that means they will work as a buffer system. Okay, so this new pH, you're going to use the Henderson-Hasselbalch equation, which is pH equals to pKa plus log concentration of salt over weak acid. Okay, so first let's calculate what is the initial mole of my ethanoic acid. So now I have 50 milliliters. Okay, so which is equal to 0.02 mole. Okay, my NaOH is just 40 over 1000 liters times with 0.2 molar. So it's equivalent to 8 times 10 to the negative 3 mole. So initially we don't have any salts. Okay, because we're going to produce. So changes in moles, again, the smallest mole. So the smallest mole now is NaOH. So minus 8 times 10 to the power negative 3 mole. In our sodium ethanoate, we are producing, so the changes is positive. Okay, so our ethanoic acid, okay, 0.02 mole initially, then we use up 8 times 10 to the power negative 3 mole. So we have remaining of 0.012 mole. Okay, so NaOH complete being used up, so 0. And we are producing 8 times 10 to the negative 3 mole of my sodium ethanoate. Okay, so we have to find out what is the final concentration of both our weak acid and salt. Okay, so the total volume of the solution now is 40 milliliters initially, plus with another 50 milliliters from the acid. So in total, we have 90 milliliters, which is equal to 0.09 liter. Okay, so 0.012 mole divided by 0.09 liter. So the new concentration is 0.133 molar. Okay, whereas for our salt, its concentration is equivalent to 0.089 molar. So now we're going to substitute the value into our Henderson-Hasselbalch equation. Okay, so pKa is negative log Ka, which is 1.8 times 10 to the negative 5, plus log of our salt, which is concentration of our salt is 0.089 molar, divided by the concentration of our weak acid, which is 0.133 molar. So you will get the pH to be 4.57. Okay. Alright, so let's look at the titration curve for this one. Okay, so we start with NaOH as our analyte. So that's why, as you can see, the titration curve begins with initial pH around 13. Okay, which is the initial pH of your NaOH. Okay, then the titration curve slowly goes down, okay, until it reaches the pH jump, which is the pH jump between strong base with weak acid is 7 to 11. Okay, and the pH at equivalence point, this one will produce basic salt, so it's more than 7. Okay, so at equivalence point, I need 20 milliliters of my ethanoic acid, so it's been labeled with the equivalence point. Okay, and after reaching the equivalence point, we have completely used all the NaOH present in the solution. Okay, and all the NaOH has been converted to produce the salts, and we add more CH3COH, our ethanoic acid, so we have excess CH3COH. So now in the conical flask, it's a combination of CH3COH with its salts. So that's why after equivalence point, we have this buffer region. Okay, so the pH of the final solution will never reach, will never go across the pH of our initial, the initial pH of our titrant, which is around 4.5. Okay. So let's look at the last example, which is between strong acid and weak base. So I'm going to use hydrochloric acid with ammonia. Okay, so hydrochloric acid, this one serves as my analyte. and my ammonia serve as my titrant. So you're going to see your pH curve starts from pH below than 7 and it's going to end at pH above 7. So this one, okay, so between strong acid and weak base, so the pH jump is between 3 to 7. Okay, so equivalence point, the pH should be less than 7. Alright. Okay, so you have to calculate first the initial pH of your analyte, which is our HCl. Okay, so HCl is a strong acid, so it completely dissociates in water, releasing our H3O+. Okay, so whatever the initial concentration of my HCl, okay, is going to change completely to form our H3O+. Okay, so pH equals to negative log H3O+. So negative log 0.1, which is equals to 1.0. So that is the initial pH of our analyte. Alright, so let's look what if I added 10 milliliters of my ammonia. So you need to calculate what is the initial mole. So my ammonia, 10 milliliters over 1000, we convert to liters, time with the concentration, which is 0.2 molar. Okay, so this one is equals to 2 times 10 to the power of negative 3 mole. Okay, my acid is 40 milliliter over 1000, convert to liters. So it's equal to 4.0 times 10 to the power of negative 3 mole. Okay, so NH4Cl is being produced, so initial is negative 0. So changes in mole is the smallest mole. Okay, so my smallest mole is ammonia, so negative 2 times 10 to the power negative 3 mole. And we produce ammonium chloride throughout the titration reaction or neutralization reaction. So positive here for changes in ammonium chloride. And remaining mole is simply the additions of 2, so 0. This one becomes 2.0. Okay, so final volume of the solution is actually, we have 40 ml of HCl plus with 10 ml of NH3. So total 50 milliliter, which is equal to 0.05 liter. Okay, so final concentration, okay, for HCl is 2.0 times 10 negative 3 mole. Okay, over 0.05 liter, which is equals to 0.04 molar. And this one, okay, since we have a combination of hydrochloric acid and ammonium chloride in the solution, so hydrochloric acid is not our weak acid. Okay, so it our weak base, so it cannot work as the buffer system with its NH4Cl. Okay, so the pH is just simply negative log H3O+ concentration. So this one is a strong acid, so whatever the concentration of HCl is present is equal to the H3O+ concentration, because 1 mole of HCl will produce 1 mole of H3O+. So the pH after additions of 10 ml of ammonia is 1.40. Okay, so what happened at equivalence point? Okay, so ammonium chloride is made up of NH4+, which is conjugate acid from weak base ammonia. Okay, so it will hydrolyze again in water. Okay, so let's write down the hydrolysis equation. So in the process, it's going to produce H3O+ equals, so this is a properties of acid. So that's why the pH is less than 7. So Cl negative, your chloride ion is an anion from strong acid HCl. Okay, therefore it will not hydrolyze again in water. Okay, so what is the volume of ammonia needed for equivalence point to be reached? Okay, so we have 0.1 molar of my strong acid, okay, multiply with 40 milliliters of the volume over, okay, we use 0.2 molar of ammonia, so volume is to be found and 1/1. Okay, so cross multiplication, so you will get ammonia needed is 20 milliliter. So means after additions of more than 20 milliliters of ammonia, so now after 20 milliliters it already reached the equivalence point. Now we have excess ammonia and ammonium chloride in the product, so it's going to work as a buffer system. Okay, so now we have 55 milliliters, so we only need 20 milliliters of ammonia for equivalence point to be reached. So that means that another 35 here is in excess, okay? So they will work as a buffer system. That means you're going to use Henderson-Hasselbalch equation to calculate the new pH, okay? So this is a base, so we're going to use POH equals to PKB plus log concentration of our salt over concentration of our weak base. Okay, so let's calculate first the initial mole of both of ammonia, HCl and ammonium chloride. So ammonia we use 55/1000 liter time with 0.2 molar. So the initial mole is 0. Okay, so our hydrochloric acid is just 40/1000 liter time with 0.1 molar, which is 4 times 10 to the power -3 mole, and ammonium chloride is going to be produced, so initial is 0. So changes is the smallest mole, again smallest, let's write down here. Okay, so the smallest now is HCl, so minus the number of mole of HCl. Okay, but we are producing ammonium chloride, so the changes here is positive. Okay, so remaining mole is just you subtracting the addition of initial with the changes, okay. Okay, so we add 40 ml of HCl with 55 ml of NaOH, so the final volume is 95 milliliter, which is equal to 0.095 liter. Okay, so final concentration is in the weak base and ammonium chloride. Okay, so the final concentration for this one is 0.0737 molar, and for my NH4Cl is equals to 0.0421 molar. Okay, so then you can substitute the value into your Henderson-Hasselbalch equation. So POH equals to negative log Kb log concentration of our salts, which is our ammonium chloride, okay, over concentration of our weak base, which is 0.0757 molar. So your POH will be 4.50. Okay, so pH is 14 minus POH, so 14 minus 4.50, which is equals to 9.50. So the new pH after additions of 55 milliliters of my ammonia is 9.50. Okay, so let's now look at how does the titration curve looks like when we are titrating our hydrochloric acid with ammonia. Okay, so it's going to start from below because we start with our strong acid, which has initial pH of 1. Okay, so it will slowly to increase with a sharp increase at the pH jump, which is between 3 to 7. Okay, so equivalence point is in between, and we need 20 milliliters of my ammonia for the equivalence point to be reached. So you're going to label the pH is about 5. Okay, with the volume of NaOH needed is 20 milliliters. And after that equivalence point, we have excess. Okay, so at this region, we have excess ammonia plus NH4Cl, which is being produced from the titration between HCl and H3. So since we have this combination, so they work as a buffer component. So that's why in the titration curve, you can see a buffer region which shows slow changes in the pH. Okay, so we are done with the calculation. So I'm going to leave you with a new quiz, which is your quiz 7 Okay, so the titration is between your ammonia, which is your weak base, with sulfuric acid, which is your strong acid. In this quiz, you're going to use ammonia as your analyte. Okay, so please make sure you try to answer this quiz 7, and we're going to discuss again in our tutorials on week 18. Okay guys, thank you for watching this video. Okay, see you guys again in my last video for chapter 7, which is about solubility. Bye bye and take care.